So after difference of metallic conductance and electrolytic conductance and factors affecting conductance and resistance, let us come to resistance and conductance. So resistance, pretty obvious, directly proportional to length, inversely proportional to area, and proportionality constant to be removed, and then resistivity will be the constant, that is specific resistance. So R will be equals to resistivity length upon area, right? And resistivity can also be calculated by the same formula, R that is resistance, A that is area upon L. Okay, so conductance, coming to conductance is 1 upon R, that is 1 upon resistance. Okay, and ohm inverse is its unit, and Siemens can also be its unit, like ohm inverse is equals to Siemens. Okay, so conductivity or specific conductance is 1 upon resistivity, simple as that. The same goes with conductivity and resistivity, and conductance and resistance. So resistance was equals to resistivity L upon A, so conductance will be equals to L upon R A, right? So L upon Ra will be equals to conductivity, that is shown by kappa and italics K. Okay, so 1 upon resistivity is shown, 1 upon resistance is shown by G, that is conductance. So conductance is equals to 1 upon R, kappa that is conductivity, that is equals to 1 upon resistivity, or G L upon A, where G is 1 upon R, that is conductance. L upon A is the cell constant. Cell constant, we can put any of the constant to represent cell constant, but the value is obviously L upon A. Okay, don't get confused. Resistance is resistivity into L upon A, right? Resistivity is R resistance into A upon L. Okay, conductance is 1 upon resistance, that is shown by G, capital G, while conductivity is 1 upon resistivity, that is shown by kappa, italics K, and it is also written as L upon Ra, where L upon A will be known as cell constant and 1 upon R will be conductance, shown by capital C. Okay, so आपका कप्पा is directly proportional to number of ions or number of charged ion. Okay, so here comes a very important new term, that is molar conductivity or molar conductance. This is shown by lambda and subscript m. Okay, so molar conductivity of a solution containing 1 mole of electrolyte between 2 electrode which is 1 centimeter apart will be molar conductivity. See, molar conductivity is directly proportional, will be equals to what, say, your kappa, that is conductivity, right, multiply by volume. Okay, so we can also write volume as C, that is molarity upon 1000. How come? We very well know about molarity's formula, that is number of moles divided by volume of solution in liters, right? So here for molar conductivity 1 mole is given, so N will be equals to 1, and coming to our volume which is to be found, right? So here we will be giving V, so V will be equals to 1000 upon C. So therefore molar conductivity is calculated by the formula kappa into volume, so that can also be written as kappa into 1000 upon C, which is molarity. C is molarity. Its unit will be ohm inverse, that is kappa 1000, that will give us centimeter square, and C upon 1000 will be centimeter square mole inverse. Simple. Now equivalent conductance is to be found, so it will be pretty simple that instead of molarity you will be using normality. Now we will be taking a new topic, that is a variation of conductivity and molar conductivity with concentration. So this is not basically a new topic but a part of molar conductivity only, but we get confused a lot in this particular. So the point is that with concentration, how come is the conductivity and molar conductivity will be varying, right? So conductivity will be the entire conductivity of the electrolyte, right? And molar conductivity will be the conductivity taking place per unit volume, right? So conductivity will always decrease when the concentration will be decreasing, okay, of both, for both the cases, strong electrolyte and weak electrolyte. It's pretty simple, pretty obvious. If the concentration of ions will be decreasing, the conductivity will be obviously decreasing. Coming to molar conductivity, the case is bit reversed in this. What it is that with decrease in concentration, the molar conductivity increases. This is because the total volume of the solution containing 1 mole of electrolyte will also be increased. Okay, so in case of molar conductivity, it is inversely proportional to concentration, while simple conductivity, it is directly proportional to concentration. Okay, when concentration approaches to 0, so molar conductivity is also known as, should be known as limiting molar conductivity, and it will be represented by the symbol lambda naught. Okay, so if we get on both the electrolyte one by one with strong electrolyte as the initial one, we will get to know that whenever, see, dilution is a process by which you can decrease the concentration of ions, okay, the charged particle present in any electrolyte, simple as that. So as you increases dilution, that means as you lower the concentration of charged particle in any strong electrolyte, so your molar conductivity will be increasing slowly. So we can put it in this way: for strong electrolyte, molar conductivity increases slowly with dilution and can be represented by the equation molar conductivity will be equals to limited molar conductivity minus A, that is a constant, multiplied by C, that is concentration, 1 upon 2 upon, right? So the value of A, that is the constant for a given solvent, and temperature depends on the type of electrolyte. Okay, so again we repeat the equation for the strong electrolyte for the relation of lambda and dilution and concentration will be lambda will be equals to lambda naught minus A under root of C, where C is concentration, lambda naught is limiting molar conductivity, lambda is molar conductivity. Okay, and if we plot a graph between your molar conductivity and under root of C, that is concentration, we will be getting a negative slope, okay, and a steep graph, straight line graph. Okay, coming to weak electrolyte, it will be the same in the weak electrolyte also, but in this case will be that on the change in lambda with dilution is due to the increase in number of ions in the total volume of solution that contains 1 mole of electrolyte. Okay, so here is the reason why lambda at dilution will increase. Okay, what dilution will take, when dilution will take place, your concentration of ions will be decreased, hence lambda will increase. So in the case of weak electrolyte, the graph shows a steep curve. So therefore, if we place molar conductivity as lambda at y-axis and under root of C at x-axis, we are going to have a rectangular hyperbola as the product or as a graph. Okay, but at infinite dilution, where C will be approaching 0, the electrolyte will dissociate completely. Okay, so dissociation constant will be equals to 1. Okay, so now effect of electrolytes will be in the next audio. Till then, bye bye.